Namaste everyone, and welcome. Cello, let's dive right into this fascinating explainer, where we're going to literally unravel the mysteries of how we measure the world around us. We're going on a bit of a journey today, all the way from those kind of confusing, chaotic, ancient measurement tricks, right up to the absolute, undeniable rules of physics and motion. If you've ever wondered how humanity figured out how to build things with such crazy precision, or how we know if something is actually moving or just chilling there, well, you're in exactly the right place. Let's get started.
So, to kick things off, I've got a question for you. Have you ever heard a local tailor, or maybe even your grandparents, throw around old terms like char angula? Literally, it means the width of 4 fingers. But think about that for a second. If someone tells you to add char angula to the length of a kurta or a piece of wood, what does that actually mean? I mean, is your char angula the exact same width as my char angula? Definitely not, right? This exact question is the root of a massive historical headache, and it's exactly where our kahani begins today.
To really see this in action, let's talk about Deepa. She's an 11-year-old student from Haryana, and she literally just had this exact char angula experience. She had a bit of a growth spur over the summer and needed a new school uniform. When she went to the tailor with her mom told the Masterji to increase the length by, you guessed it, char angula. Now, Deepa is a pretty curious kid. She noticed the tailor was using this floppy, flexible tape, but earlier the cloth seller had used a rigid metal rod. This simple observation sparked a massive, full-blown debate in her classroom about how we actually measure things.
So here is our roadmap for this explainer. First, we'll tackle the measurement problem, then look at standard SI units as the fix, and go over using scales correctly. After that, we'll shift gears to ask, what is motion? And wrap up with the types of motion. Cello, let's move.
All right, Section 1, the measurement problem, or why using our body parts to measure stuff is a terrible idea. The absolute main thing we need to get straight right away is why relying on our own hands and feet to measure things is a recipe for total chaos. I know, it sounds super convenient, right? Your hands are always with you. And honestly, India has a rich history of this. Back in the day, people used the angula, the finger width, or a farmer would literally just walk his field and count his strides to measure it. Even today, you'll see carpenters and tailors using these tricks. But here's the massive flaw. What actually happens when 2 different people try to measure the exact same thing?
Well, let's look at what happened when Deepa and her friends, Anish, Padma, Tasneem, and Hardeep, decided to test this out. They measured the exact same classroom desk using their handspans. Check this out. Padma got exactly 13. Hardeep, he got 14. Deepa was stuck somewhere between 13 and 14. They measured the exact same table, guys, but because their hands are all different sizes, they got completely different answers. Imagine trying to build a house or trade expensive silk using this method. It's confusing, it's messy, and it proves exactly why we desperately needed a better way.
Moving on to Section 2. Standard SI units, the ultimate global fix. So as people started traveling and trading across borders, this whole handspan confusion became a serious global issue. The world desperately needed a universal language for measurement. Basically, countries from all over the globe had to sit down and agree on one single standard. And that's what we call the International System of Units, or SI units for short. Thanks to this system, a meter in India is the exact same length as a meter in Japan, or Brazil, or Canada. No debate. The SI unit of length is the meter, written with a lowercase m. We use kilometers for long distances and centimeters or millimeters for the tiny stuff. It completely eliminates all that guesswork, no more relying on someone's random foot size.
But wait, even with standard units, you've still got to have the right tool for the job. Think about it. Why do we have those flexible tailor's tapes and rigid geometry scales if they both measure in centimeters? Well, try measuring the trunk of a tree or your chest with that stiff plastic scale from your pencil box. Yeah, that's not going to work. You need the flexible tape for curves and the rigid scale for perfectly straight lines. Choosing the right tool is literally step number 1 for getting things right.
Section 3. Using scales correctly, because your technique totally matters.
Listen, having the world's most accurate fancy ruler is completely useless if you don't actually know the proper technique to read it. Yes, there is a right way and a very wrong way to use a simple scale. Let's walk through the exact steps to get a perfect, precise measurement every single time. Step 1. You must place the scale directly in contact with the object, perfectly parallel along its length. If it's tilted even a tiny bit, boom, your measurement is ruined. Step 2, and honestly, this is where almost everyone messes up, you have to position your eye directly above the tip of the object where it hits the scale. If you look at it from an angle, from the side, the markings are going to look shifted. It's a classic optical illusion. So scale flat against the object, and your eye looking directly straight down. That's how you get that perfect precision.
All right, Section 4. What is motion? Let's figure out how we actually define movement.
Okay, let's totally shift gears here. We've mastered measuring things that are just sitting there. But how do we scientifically describe when something actually moves, like changes its position? It sounds like a no-brainer, but physics has a very, very specific way of looking at this. The absolute foundation of all movement is something called a reference point. A reference point is simply a fixed object or a spot that you use to compare against something else. By definition, an object is only in motion if its position changes with respect to that reference point over time. Basically, without a reference point, motion doesn't really mean anything. It is 100% dependent on your perspective.
Let's do a quick thought experiment to really prove this point. Imagine you're chilling inside a moving bus. Are the other passengers sitting near you in motion, or are they at rest? Well, if you use yourself or the bus seats as the reference point, those passengers are completely at rest, right? They aren't moving away from you. But if your reference point is a building outside the bus window, then suddenly you, the bus, and everyone inside are zooming by at 60 kilometers an hour. See, it all depends on the reference point. Here's another crazy one. Imagine being in a ship on a perfectly calm sea, inside a room with absolutely no windows. Without being able to see a reference point outside, you literally wouldn't even be able to tell if you were moving. Mind-blowing, right?
And finally, Section 5, Types of Motion. How we categorize different kinds of movement.
So once we've locked in our reference point and figured out that an object is for sure moving, science lets us categorize exactly how it moves. The first, and honestly the most straightforward type, is linear motion. Think about an orange detaching from a tree branch. It doesn't do a little loop-de-loop or zigzag on its way down. Gravity just pulls it straight down to the earth. Whenever an object moves along a perfectly straight line, that, my friends, is linear motion.
Another awesome everyday example of linear motion? Think of students marching together in a parade, or maybe during your school assembly. As long as they are moving straight ahead down the path, without taking any turns or curves, they are perfectly demonstrating linear motion. It's direct, it's straight to the point, and it's super easy to measure.
But hey, things in the real world don't always move in perfectly straight lines, do they? Nope. And that brings us to circular motion. Look at this fun little experiment you can actually try yourself at home. If you tie a small object, like an eraser or maybe a small potato, to a string and just whirl it around in the air, what happens? It traces a circle. The object is constantly changing direction, but it's staying at a fixed distance from your hand, and your hand is acting as the central reference point. That right there is the textbook definition of circular motion.
Finally, we've got oscillatory motion. The official definition here is moving to and fro about a fixed position. A bit wordy, I know, but to picture this, just imagine a playground swing. When you pull it back and let it fly, it swings forward, then backward, passing right through that bottom resting point over and over again. It's a repeating back-and-forth rhythm. A grandfather clock pendulum does the exact same thing. That rhythmic to and fro dance, that is oscillatory motion. So we've gone from the super confusing handspans of the past to the absolute precision of the metric system, and finally unlocked the secrets of how things move, whether it's in straight lines, circles, or cool oscillations. Now, before we wrap up this explainer, I want to leave you with a bit of a challenge. Look around your room right now. Seriously, look around. What objects are in motion depending on your reference point? Is your ceiling fan up there demonstrating circular motion? Maybe you have a clock pendulum oscillating. Or hey, are you actually moving right now relative to the sun? Think about it. Start applying these physics concepts to your own world and just keep questioning how everything around you measures up. Thanks so much for hanging out with me for this explainer, and I'll catch you guys next time.